Thanks, Michael. Sorry, guys. Oh man, I gave such a beautiful speech. You should have heard it. Godverdomme. I'm sorry. It's still early for me as well. Shit. Let me start over. Good morning, guys. Also, everybody on YouTube. Sorry. Uh, oh, on the agenda, on the agenda today, we start with a recapping the replicating portfolio to price a call option in a binomial setting, so in a setting where the underlying can only go up or down by a certain amount. And we extend it immediately to 2 periods. After this, I show you a second method, also still in a binomial setting, risk-neutral pricing. Like I said in our Telegram group, I think I thought yesterday about a neat way to explain it. So there's no real need to worry about it. You will see the intuition will check out. And if you say, well, you struggle with intuition, I still want to say on the record, there's a neat cooking recipe. So you can really go through the same steps and it will always work. And once we have established this, then, if we still have time, we do Black-Scholes. And you might think now, wait, did he not yesterday say 2 things? Black-Scholes is the model for option pricing in the real world. And secondly, did Mr. Black and Mr. Scholes not win a Nobel Prize for their mathematic approach? Yes and yes. So how can we do this in a couple of minutes? Well, that's the whole reason why we go through those unlifelike models first. To transfer our knowledge then to Black-Scholes will be like this. We don't need to be able to mathematically derive it. We need to be able to apply it and we need to be able to interpret it. And that is not rocket science, as you will see. So there's no need to be worried about today's class. Before we hop in, are there any questions? Is there anything I need to address before we dive in? Super. Okay. Cool, guys. Like yesterday, please, you know I love it that you have advanced questions. And also yesterday after class, I got so many WhatsApp and Telegram messages building already on what we've discussed yesterday. So my main worry was, will the guys understand what we're discussing? And many of you are very well beyond what we have already discussed. So that's really cool. I found myself yesterday sending a lot of messages. I mean, if you think about this stuff, then you might want to look into the Master of Finance. So yeah, I'm super optimistic. I'm excited to do this. Let's. So we have discussed the replicating portfolio yesterday. Before we do any details, what is a replicating portfolio about? What's the conceptual reasoning behind it? Well, the reasoning is this. We're looking at a weird instrument, an option, a call option to be more specific, and we don't know what should the price of this be. Which price tag should we attach to it? And it's very difficult. So how should we approach it? Well, what we could do is we could look at what will the future payoffs of this weird unknown instrument, what are the payoffs gonna be in the future? And then we take a basket and put financial instruments in the basket of which we know the actual prices that are easy to price or easier to price. And the combination of these instruments together perfectly replicates the payoffs of the instrument that we're trying to price, the call option. And then the reasoning is, well, if the basket of known financial instruments perfectly replicates the cash flows of the unknown instrument, the call option, they must have the same price. And why is that? Based on the law of one price, they have to have the same price. Otherwise, there would be an arbitrage opportunity. Don't forget, arbitrage is complicated finance, blah, blah, for making profit without risk. So simply exploiting only temporary existing price differences. Think of my example with an ounce of gold in Amsterdam versus an ounce of gold in Shanghai. So that is the core logic of the replicating portfolio. And we then also discussed, well, how does the replicating portfolio specifically of a call option look like? Well, it's very simple. What do we have to do to replicate the payoffs of a call option? We need to buy a certain amount of shares, of the underlying shares, not any, of the underlying shares of the call. And we need to borrow a certain amount of money. The number of shares we need to buy, we call delta. The amount of money that we need to borrow is called B. That's all there is. We set up then our replicating portfolio by buying delta shares and borrowing an amount of money B. And we set up the equation that this replicating portfolio has to equal the two different payoffs of the call option in the future. Then we end up with a system of two equations, up movement and down movement. We calculate delta first. Delta is calculated immediately and easily by swing of the call divided by swing of the underlying, swing of the share. Once we have delta, we fill in delta in either of the two equations and solve for B. That's then the replicating portfolio. And if we then go back to T0 and fill in the actual stock price, we really get the option premium of a call option. That's what we did yesterday. Today we start with exactly the same thing. The only difference is we now extend it. We are saying the option does not expire one time period from now, so 1 year later, let's say, but 2 time periods. It's the same steps. There's nothing to be worried about. It's literally the same thing, only longer, all right? So we use the exact same example, same values, everything. We still have an interest rate of 11%. We still have a call option with a strike of 50. We still have a current stock price, the price of the underlying of 50 as well. And the price movement of the underlying asset is given to us again as a binomial process. So that's not something I've calculated. This here must be given to me or I cannot do it, okay? So don't obsess over those numbers. Where are they coming from? It's part of the example. Again, I said it yesterday and I want to say it again until you start making jokes about it, really. This 50 here is not the same 50 as here. This is the strike price, also known as the exercise price. And it's just a coincidence that the price of the underlying right now is also 50. So when you do calculations in this context and you see the number 50, make absolutely sure that you conceptually understand, am I looking at the price of the underlying or is it a strike price? So that's why I was so obsessive and maybe in your view strict when we drew our payoff diagrams, that you know the terminology well and that you understand the reasoning. What's a call? It means to buy the right to buy for a strike price regardless of the price of the underlying, okay? Please don't confuse these two. The questions that we have to address, the same as yesterday, the same two. Which replicating portfolio will mimic the cash flows of this specific call option with a strike of 50 perfectly? When somebody says, which replicating portfolio, blah, 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 the answer has to be basically two numbers. How many shares do you need to buy? So what is delta? How much money do you need to borrow? So what is B? And secondly, what's the price that you will pay for the call option? So that means we need to fill in the actual values for the share price in our replicating portfolio and actually calculate it. That's it. Let's do it. So this is the binomial process. Binomial because from each period to the next, only two things can happen. The current stock price is 50, that's the underlying 50. That is not the strike price, okay? That is S0. What can it do from here to the next period T1? Either it goes up from 50 to 70, or it goes down from 50 to 35. So let's say it goes up. We have an up movement. What can it do then one period later at T2? Well, from 70, it could increase one more time. So then we have two up movements from 70 to 100. Or it can go down again from 70 back to 50. It could also be different. It could, starting point is 50. It could go down from 50 to 35. What can it do then? Either go up to 50, same level as before, or go down one more time from 35 to 25. In case you're wondering now a little bit about the values, they are really arbitrary, right? So there's no specific logic to it, so don't be weirded out that you say, now wait a second, here from 50 it decreases by 15 to 35, and here it only decreases by 10 from 35 to 25. There's no reasoning behind this, right? There are just estimations, predictions, and overall, let's not forget, this is a simplified model. This is not real world, okay? This is warm up, foreplay, so that we then understand Black-Scholes, okay? So don't obsess over this, please. Okay, how do you solve something like this? Well, you've already seen it yesterday when we only looked at this part here. The way to solve this is you have to come from this side. You start here and work your way backwards to the origin, to t0. And the same is still true. So what we will do is we have to approach in our solution from this side and solve separately and work again our way backwards. There is something I need to, that's not really a finance explanation, that's terminology, otherwise we cannot really talk about it. Let me do this quickly. Have a look. No. So, all right. Okay. Okay, have a look at this. So this part of the tree, let me sketch this out here quickly. So this is basically a compass. So this part of the tree we refer to as the northeastern part of the tree. That's not finance terminology, it's just that we know which part we are talking about. Okay? Logically then, this part of the tree we refer to as southeastern part of the tree. And last but not least, when we have done that, in the end, we have a third calculation where we then go back to the origin. Okay? So, and that is also reflected on my slides. I have not always have the space, I don't have the space to always show the whole tree on each slide. So we start with the red outline first, so the northeastern part first. Step 2, the green part, so the southeastern part. Once we have those two figured out, in the last step, the blue part, we go back to the origin. Okay? That's the structure of the slides as well. Let's do it. Let's do this. Okay. Yeah, like I said, we work our way back from the end of the tree, starting in the northeastern part. So this is just repetition, there's nothing new here. Once we have the numbers, of course, we go back to it, right? So this is the northeastern part of the tree. Of course, you can go back one slide and just that you see the whole tree, this is top right. Where the stock has already increased to 70, and so that's T1, right? So what will it do? Either the underlying goes up to 100 or it goes down to 50. And we approach it in exactly the same way as a one-period model. We ask ourselves, step 1, what would be the payoff of the call in this scenario? What would be the payoff of the call in this scenario? So we can set up our two equations that will help us define our replicating portfolio. And that is why you need to have a good understanding of options basics. So what's the payoff of the call here? Well, if the underlying at T2 has a value of 100 euro and you have a call with a strike of 50, it means you have the right to buy it for the strike of 50. So you hand over 50 and you get back an underlying with a value, a stock with a value of 100. What is the payoff then? Price of the underlying minus the strike you had to pay. So 100 minus 50, and that is, boom, 50. Value of the call, 50 here. That's where the 50 is coming from. Don't confuse this 50 with a stock price at T0, which is 50, and don't confuse this 50 with a strike price, which is also 50. Okay? All right. What happens if the stock price goes down from 70 to 50? Same reasoning. What's the payoff of the call in the scenario where the underlying has a value of 50? Would you exercise yes or no? Doesn't matter. So what's the value of the call then? It would be 0. You have the right to buy something for the strike of 50, which you can buy anyway for 50. That's why the value of the call here is 0. Okay, once we have the two payoffs, we can set up our equations. Boom, that's what I'm doing here. Okay, so we need to buy delta shares and borrow an amount of money B. Okay, so I set up delta multiplied with share price in the up scenario. Delta times 100 minus 1 plus interest rate, yeah, that's of course given to us, multiplied with B. Why this term here? don't forget, we borrow the amount of money B right now at T0. So we need to, or in this example, one period earlier, that's of course T1, but it's still one period. So that means I will have to pay back the amount I borrowed B, but including interest. So that's what I'm doing here. B multiplied with 1 plus interest rate. And since I have to pay it back, I get a minus here. That's the reasoning. And I want it to be a replicating portfolio. I want it to replicate the payoff of the call in the up scenario. So that's why I set it equal to 50. The 50 here is the payoff of the call. It is not the price of the underlying at T0, and it is not the strike price. The 50 that you see here is the value of the call, the payoff of the call. We replicate payoffs, okay? Please don't confuse this. And we do the same thing, set up the replicating portfolio after one down movement. So that's what I'm doing here. Again, we buy delta shares and we borrow an amount of money B. So delta multiplied with the share price in the down scenario. That's 50. I hate to do this to you guys, but the 50 here is not the payoff of the call. It is not the price of the underlying at T0. And it is also not the strike price. The 50 here is the share price, the price of the underlying after this down movement at T2. Okay? So please don't confuse this when you later on review it. Make sure when you look at a number that you know exactly what this represents. Okay? So delta times 50, the share price at T2, minus amount of money that we borrowed B, including interest again, and we wanted to replicate the payoff of the call. The payoff of the call in this down scenario, as we figured out, is 0, so I set it equal to 0. How do I solve then for delta and B? Delta is calculated as swing of the call divided by swing of the underlying, so I solve for delta. Once I have delta, I fill it in either of the two equations. I would pick the one with 0 because it's easier. And I solve for B. So I have not put this on the slides anymore because that's just simple equations. But we end up now with a delta of 1 and we end up with an amount of money that we have to borrow of 45 euro. What does this mean in a full sentence? Well, this part of the call option you could replicate by purchasing one share, one of the underlying shares, by borrowing 45 euro. Okay? All right. Okay. Look at the reasoning in the second bullet point here. We say then, okay, you borrow 45 euro out of the 70 that you would need in order to buy one share at T1. The share price here is 70 and we borrow 45. Okay? So, what is then the value of the call at this point in time? That's not complicated to figure out. The call must have a value of 70 times 1. What's the 1 here in my calculation? That's of course delta, right? Minus, what's the 45? That is of course B. So I simply fill in the values that we have calculated. And I press the button and I find value of the call here, or payoff I should say probably, 25. Okay, I made here a small note, compare this to slide 15. If this step is a bit too quick, that's exactly what we did before as well. All right? Okay, let me go back. No, sorry. Let me go back, yeah. So we have done now the northeastern part, this here. We have figured out the payoff of the call at T1 now. So we need to do exactly the same thing now for the southeastern part of the tree, this one here. It's exactly the same thing. Southeastern part, the share price here starts at 35 and either goes up to 50 or it goes down to 25. Typically the southeastern part is my favorite part because you will see in a second why. The underlying here has a value of 50 and we have a strike of 50. What's the payoff therefore of the call? 0. What is the payoff of the call in the scenario where the stock price decreases to 25? Also 0. So I can set up my replicating portfolio, delta times share price of 50. Again, I spare you the whole speech. It's this 50, okay? It's the stock price after one down movement and one up movement. Don't confuse it with anything else. Minus amount of money borrowed B and including interests, and we set it equal to the value of the call, equals 0. And I do exactly the same thing here, delta times share price at T2, the 25, minus B, including interests, equals payoff of the call, 0. The reason why I like the southeastern part of the tree in binomial exercises, typically you end up with a lot of zeros here, so that it's super easy to solve them. And I'm lazy. That's really the only reason I like it. So we solved then the two equations exactly like before. What is delta? Swing of the call divided by swing of the underlying, swing of the share. And we find delta equals 0 and B equals 0. So you see already why I like this so much. So how can we replicate the payoffs of the call here? Let me put this in words now. We can replicate the payoffs of the call here by buying no shares and borrowing no money. That's it, okay? I switch my phone on mute, sorry. Whoop. Absolutely. Shoot.
Well, first of all, in the past example, we had a value of a call from 50 and one of 0. Is 50 like from S0 to S2 and then like 100 min 50?
What? I don't get it.
Yeah, like we were looking at the northeastern part, right? And
Yeah.
then you have like S1 is 70 and S2 was 100 in the first example. And then there was like in the upper part of the northeastern part, there was like the value of the call is 50, but where does that come from?
Okay, wait. Northeastern part. So the northeastern part is this here, right?
Yeah.
You mean this, the 50 here?
Yes.
Okay, so where is that coming from? You have a call option. Let me go back to the actual definition of the exercise. A call option has a strike of 50, right? A strike means the price that you may purchase the underlying in 2 time periods from now on, from me. So you can call me, hey Flo, I want to exercise the call, and then you have to give me the strike, 50, and I give you back the underlying, no matter what the actual price of the underlying in 2 periods in the future is gonna be, okay? So here the share price goes up and up, so that's why we end up here with a share price of 100. But you, Storm, hold the right to buy it from me for the strike of 50. So at this point, you would look at the share price and say, wait a second, it's traded for 100 and you hold the right to buy it for 50 from me. So you would then say, hey Flo, I want to exercise, you give me 50 euro, I give you back the underlying, which is then traded for 100. What would you do with the underlying? Immediately sell it for the current market price of 100. So what would your payoff then be? Underlying minus the strike. So 100 minus the strike of 50. So what is the payoff of the call then? 50. Make sense?
Yes.
Super.
And
Yeah.
I also had one little question about the second example.
Shoot.
Where like at the end you say like the value of the call must be 0 at the bottom of the calculations. Is that like S1D or is it like CD? How do you explain that?
Do you mean these 2 zeros here?
No, the 0 at the last sentence.
The 0, this here. The call must therefore be worth 0?
Yes.
Okay, the 0 here I get simply by calculating delta equals 0 and B equals 0. And if you look at the replicating portfolio equation here, delta times share price minus blah. So the moment you fill in a 0 for delta, this here becomes 0. Then you end up with 0 minus all of this. But if B is also 0, the whole term here becomes 0 as well. So you end up with a calculation that says 0 minus 0. That's just all 0.
Yeah, right, but there's not like, how do you call it, like a variable that is like the 0 at the end. Like it's just the worth of the call, but it's not like S1 or
No, no, exactly. That's just the payoff, the value of the call indeed, yeah. It's exactly, so the 0 here, maybe that helps to understand, the 0 here, the call must therefore be worth 0. It's the same kind of number as we had here 25, okay? So that's the value of the call in this scenario then, when you solve the replicating portfolio equation with actual values for delta and B.
And I think in the Western scenario, it would be CD. So the value of the call if the price went down.
Wait a second, we don't have any Western scenario, we only have Eastern scenarios.
No, but I mean like in the last one.
From yesterday.
Yeah, like in the decision round 1, basically.
What's the question?
No, because I think Storm wanted to know like what kind of variable the number could be assigned to.
Ah, okay. Thanks. Yeah, thanks, Michael. I understand. Yeah, thanks for explaining. Got it. So I went back now to the example from yesterday. So when you asked Storm, what does the 0 that you were referencing represent? The price of the call option. In our yesterday's example, we ended up with a price of 10.57 at a specific point here. And now we have calculated the price of a call at a different point in a different scenario, and our result was 0. So that would be the price tag of the call. But since it's a 2-period model, don't obsess over it too much because it's an in-between result. We are not back at the origin yet, so there's no real smooth interpretation in my view. Okay? But it would represent the value of the call at this point.
Yes, clear, thank you.
Nice. Okay, all right. That was the northeastern part and the southeastern part. So that means we have now figured out the value of the call for this point in time and for this point in time. And that's what we need to get to the origin. So what we have left now is exactly the step from yesterday. One last calculation. Let's do it. Huh?
Why is delta 1 in the northeastern part and why is it 0 in the southeastern part?
I'm not sure how I should answer that question. It's a matter of solving the equations, right? So if you set up your equations, replicating portfolio number 1, replicating portfolio number 2, and then you solve for delta and B, that are the values that you will get.
But how can you solve delta? How can you solve 2 missing variables? Because you
It's a weird question because I know for a fact that you have attended yesterday's class, right?
Yes.
Okay, then very briefly. So rewatch yesterday's class, but I cannot leave it unaddressed. This is how you calculate delta, swing of the call divided by swing of the share. Right?
Yeah.
Yeah. That's it. Okay? All right. So, okay, we go back now to the origin of the tree. So that's of course what we want. We want to figure out the value of the call right now, not some weird future values. Okay, so the share price starts at 50 and goes either up to 70 or goes down to 35. And this is now super easy. We have everything already in place. We know the value of the call, the 25, that comes from the previous step as I'm saying here. The 25 you see here is this 25, the value of the call at this point in time. Where did I get the value of the call here? 0 from the previous step. That was the 0 that Storm and me were talking about right now. That's exactly this that you find here. Okay, so both values, you don't even need to think about it anymore. That are the results of the previous calculation. That's why we needed to do this. Everything else the same. We set up our replicating portfolio as we need to buy delta shares and we need to borrow an amount of money B. Delta times share price of 70 minus our whole amount of money borrowed B, including interests, equals, it should be a replicating portfolio, so it has to have the same payoff as the call. So that's why I set it equal to 25. What's the 25 here? Whoop, it's the value of the call. As always, whoop. And then I set up the second replicating portfolio, delta times share price, minus, again, amount of money borrowed B, including interests. I needed to be a replicating portfolio. It must replicate the value of the call here, the payoff of the call. So I set it equal to 0. It's this 0. And again, as before, we have to solve now for delta and we have to solve for B. How do we solve for delta? swing of the call divided by swing of the share. Okay, I do this and I get delta equals 5/7. That's not something you have to. You can type it in your calculator and of course get some 0 point something. That's perfectly fine. I find it in this form a bit easier to interpret. You have to buy 5/7 of a share. We get a B of 22.5. What does this mean? We need to borrow 22.5 euro. So this, the first question we can already answer. Which replicating portfolio mimics the cash flows of this specific call option expiring in 2 periods perfectly? A replicating portfolio consisting of 5/7 of one share and borrowing 22.5 euro. That's answer number 1. Question number 2 was, well, what should the value of the call be? Like the option premium. Well, let's do that.
Can I ask you a question?
Of course.
Is the value of the call the same as the price of the call option?
Yeah. Yeah. Yes. All right. Okay, so what price will you pay for this specific call today? So that question is about the option premium or the option price. It's of course the same thing. Well, we've discussed how the replicating portfolio that mimics this, the payoffs of this call, how it looks like. We need 5/7 of one share and we need a bond or a loan of 22.5. Okay, so what is the cost of setting this up? Well, you need to buy 5/7 of a share. Let me go back one slide. That at T0 has a share price S0 of 50. Okay, so that's the 50 here. That is not a strike, it's not anything. This here is S0, the price of the underlying at T0 at the point of origin. Okay, so I need 5/7 of that. So how much does it cost to buy 5/7 of a share that has a current price of 50? Well, 50 times 5/7 minus 22.5 euro. And I simply crunch the numbers and I find 13.20. So what does this mean in a full sentence? What have we calculated here? The option premium or the option price. So the answer would be, for an option as specified in this example, we would be willing to pay 13.20 euro. Okay? That's it. That is it. That's a replicating portfolio over 2 periods. So the only thing you have to do really, the same thing as in a scenario of 1 period, but more of it. So you have to be systematic. I don't experiment. I always do it in this, the order doesn't matter. You could start also here, doesn't matter. But I always start here, step 1, step 2, step 3. And I also practice it like this. I never do it randomly. I go through the same motions so that this becomes an automated thing in my mind. You see, I hope you see this at this point, that this is something you can practice to perfection. If something like this were on your exam and you do not get full points on this, it's really on you. Okay, so that's really, it's like a cooking recipe. If you cook Wiener Schnitzel 100 times, you can do it in your sleep with your hands tied. I want that you can do replicating portfolios like this. Okay? If you practice 2 periods, in total you should be able to do this in, I don't know, 5 minutes, no more, I would say. And you can do it, okay? You can just practice the steps. Write yourself a list. What are the necessary steps? Determine the payoffs of the call, set up the replicating portfolio, set it equal to the payoffs, solve for delta, solve for B, calculate the value of the call at T1. Do the same for the southeastern part and go back to the point of origin. Write yourself a step-by-step list that you can do this in your sleep. That's how that is done. This is something you don't need to be scared about. I want that if something like this in one way or another is on the exam, I want that you are really like, yes, I can do this. And you just crush it, okay? All right, that's the replicating portfolio. Let me check the time very quickly. 37, na ja. How about this? It's a bit unusual to have a bit of an earlier break, but normally I'm way over time. I think there's a logical break here now. Risk-neutral pricing is a completely different story. So if you don't mind, I would suggest we take our 10-minute break now. And then we do risk-neutral pricing. Again, we have 1 period and 2 periods. I will show you the 1 period model. And if we have time, why not Black-Scholes? Is that all right for you guys? Super. I see you then in 10 minutes for risk-neutral pricing. Perfect, guys. Tot zo. Guys, slowly come back to me. We'll continue in about a minute. So guys, let's do something. Come back to me. Let me switch the timer off. All right. So before we hop into risk-neutral pricing, I want to sketch out very quickly what the core logic is in a way I think is very intuitive, and I think you will not struggle with it at all. Let me show you. Boop. I need to close this. Exit. Yes, and we can move this. So, imagine, forget about options, forget about all of this for now. I want to talk about a brief game. So imagine I offered you a game that looks something like this. We play the game, we agree on the game now, but we will play it at T1, okay? So at T0, we talk about the game, and at T1, it's gonna happen. And the game is going to be super simple. The game is going to be this. Let me see. Yes, the game is going to be this. I have here €1, heads and tails. So 1 year from now, if you agree, I will toss the coin. And if it lands on heads, you will get from me, I don't know, what's a good number, €100. If it lands on tails, however, you have to give me, I don't know, €30. And the question is, of course, would you want to play this game? And if so, how much would you be willing to play that game with me? How would you approach this? Let me sketch it out. It's not rocket science. So first, you would calculate an expected value. So if you would assume, of course, that the coin I'm gonna toss is a fair coin. So it's not manipulated, it's not some kind of fraud, it's a real normal coin. So that means each scenario is equally likely. There are only two possible outcomes, it's either heads or tails. So the probability of each happening is gonna be 50%. So you would start by calculating an expected value by saying this, 50% probability times the payoff of 100 plus 50% probability of the other outcome plus 50% times minus €30, right? Okay, does everyone understand? This is just a normal expected value. Probability times outcome plus probability times outcome. But we're not done. Because the game is not gonna go down right now. We're gonna play it in 1 year. So what's the value of this game then right now? Easy. Divided by 1 plus discount rate equals whatever. That's what we do. Now, did everybody understand this? On Zoom, and I also want to hear some sort of confirmation on YouTube in a couple of seconds. So that's really relevant, okay? If you say, yeah, makes perfect sense, what's the value of this game? It's probability times outcome plus probability times outcome. And since this is going to happen in the future, we have to discount it. If you say you understand this, you will have zero problem, I think, with the core of risk-neutral pricing. Let's do it then. Let's do this. Okay. All right. So first of all, risk-neutral pricing is an extremely powerful method. It's not only used for options, it can be used for a multitude of different financial instruments. And don't forget, if you think options are weird, there's of course much weirder stuff in finance. So if you are interested in hardcore investment banking and working as an analyst and stuff like this, this is really something worth looking into. If you want to maybe even work in academia in finance, I mean, you can build your career on being good at risk-neutral pricing. So it is specifically used in derivative pricing. If you do the Master Finance and Investments, there is a course, it's an elective, it's hardcore, called Derivatives, taught by one of my most esteemed colleagues. This is what you will do. So if you already know you want to do a master, and if you already know you love or you're very interested in trading, especially in crazy stuff like derivatives, and you want to prepare, this is what you want to get seriously good at. What is the intuition behind risk-neutral pricing? So the core of it I already showed you. So we will set up basically a calculation like the value of the call equals probability times outcome plus probability times outcome divided by discount rate essentially. But we need the probabilities. And this is of course a very, very difficult game now. So what do we assume for starters? Well, we assume that risk can be eliminated by what is called dynamic hedging. So that means you can get rid of virtually all risk by some sort of hedging activities. And in order for that to work, we have to assume that no arbitrage is possible, so that everything is really properly priced. Okay? So just to give you an example of what I mean with dynamic hedging, eliminating all risk. If you were to short a call option, so you end up being the short call, how can you hedge this risk? So how can you eliminate it fully? You can completely get rid of the risk by investing in delta shares of the underlying asset while borrowing B. So the assumption is you can eliminate risk. Or let me put it in normal human language. We are basically creating an atmosphere, an environment in which risk is taken out of the equation completely. Right? Normally we talk about risk-return trade-off, the higher the risk, the higher the return. And now we try to eliminate all risk so that we end up in a world basically where this does not matter anymore. Okay? What does this mean then? Once we have taken out risk of the equation completely, then, of course through the hedging, that's not something we have to do, it's an assumption, then expected returns become equal to the risk-free rate for all investors. Okay. What does risk neutrality mean actually? Well, in a risk-neutral world, individuals would be indifferent to risk. It does not mean that they don't care about risk. It doesn't really mean that they are unaware of risk. It means they basically require no compensation for risk, and the expected return on all securities is the risk-free rate. If at this point you think that's all super weird, I don't know where this is gonna go, don't be alarmed. You will see this checks out, okay? So just give me a couple of minutes more. To give you an example for this risk neutrality concept, I have a brief example here. It's a bit silly maybe, but just to drive home the point. If you have the choice between these two things, what do you want to receive? Either $100 with a 50% probability and 0 with 50% probability, or $50 for sure. In a risk-neutral setting, you would be indifferent because the expected value of both would be 50. Probability times outcome plus probability times outcome. So the first blue bullet point has an expected value of $50 as the second one. So in the real world, you would of course not be indifferent. You would probably, I mean, depends on your risk appetite. You might say, no, I rather have 50 euro for sure. I'm not a gambler. So in the real world, that could be different. But in a risk-neutral setting, you would say the expected value of both is 50. I don't care. I decide by tossing a coin. Okay? All right. Sure?
What I don't get is like you're trying to get rid of all the risk, but still there's no arbitrage possibility. But like, why? Because arbitrage is like making profit without risk, right?
Yeah, but the logic here would be, we say there is no arbitrage possible, so that means there will be no price differences between the same financial instrument that anybody could exploit. That's the reasoning behind it. Okay? Okay, let's look at the actual method. Yeah, I want to show you the actual method. This is just background information. I've color-coded it. That's really for your personal pleasure. If you really want to get seriously good at risk-neutral pricing, if you already know you want to do a master or something like this, have a look at it. I think it's almost self-explanatory. I want to show you the actual method. What is the final calculation gonna be that we will have to go through when we calculate the value of the call. And it's this. This is the essence of risk-neutral pricing. Value of the call equals probability times value of the call in an up movement plus 1 minus the probability of an up movement is of course the probability of a down movement, right? Multiplied with the payoff of the call in the down movement, discounted by the risk-free rate. If you say that gives me trouble, no, that's exactly the game I've sketched out. Probability times outcome plus probability times outcome. Okay? So that's literally an expected value in the future discounted back to t0. I would understand if at this point you say, "Naya, wait a second. Sure, we can calculate the payoff of a call in the up scenario. We can calculate the value of a call in a down scenario. We can look up the risk-free rate. But where does the probability of an up movement come from? And where does the probability of a down movement come from?" And this is something you need to wrap your head around. I'll do my best to explain. These here, well, let me start differently. Maybe for starters, there might be some of you that are wondering, what does this mean, P and 1 minus P? I mean, you should already know this. This is really high school math, but I still want to reiterate just to avoid any confusion. Theoretically, this here is a different probability. This would be called something like Q maybe. Probability of an up movement is P, probability of a down movement would be Q. But I don't want to introduce a new variable here, and I don't need to. Because only two outcomes are possible, up movement or down movement. Like with my coin. If I toss a coin, it will land on heads or it will land on tails. Nothing else is possible. So if I tell you the probability of an up movement, what has to be the probability of a down movement? 100% minus the probability of the up movement, right? So it just has to be the opposite. If the probability of an up movement is 40%, the probability of a down movement has to be 60%. Okay, so maybe just to explain the term P and 1 minus P. So 1 minus P is simply the probability of a down movement, simply because P is the probability of an up movement. So that's for starters. But I want to talk about the probabilities. It's not too complicated, but I need you to understand this. So usually when I explain this, there are some students that, because we will end up calculating P. We will calculate the probability of an up movement. And then some students usually after class talk to me and say, "Super, can I exploit this for trading?" No, you can't, because this is not what is referred to as a physical probability. We are not going to calculate a physical probability of an actual up movement of the stock price. Okay? It's a risk-neutral probability. So it's a mathematical concept that you cannot really interpret. Okay, so P and 1 minus P, probability of up movement and probability of down movement of the underlying, are not physical probabilities. That you cannot, let's say if the probability of an up movement is 40%, you cannot then say, "Ah, cool, now I know the probability that the actual underlying the stock will go up is 40%. That would be a physical probability. And that's not what we're doing, all right? It's a risk-neutral probability. It's a mathematical concept. Okay, so please don't confuse a risk-neutral probability, some abstract mathematic thing, with a real-life physical probability. And ask yourself, I mean, it makes sense, right? I mean, how could I possibly, with any formula, calculate the probability of a real-life stock making a real-life up movement? That's impossible, all right? So please keep this in the back of your head. It's a risk-neutral probability of an up movement, not a physical probability. Okay, so but how do we get P? We can calculate the value of the call in the up scenario, the value of the call in the down scenario. We look up risk-free rate. All ingredients we know, but how do we get the risk-neutral probability? We get it like this. The risk-neutral framework looks like I'm sketching out here. There is an equation, of course. The risk-free interest rate expressed as a percentage equals the probability of an up movement, so P, that's the same P here, multiplied with the percentage change in the stock price in the up scenario, so if the price increases, plus 1 minus P, which is of course the risk-neutral probability of a down movement, multiplied with the percentage change in the stock price in the down scenario. So should the stock price decrease? And then I can actually solve this because I know risk-free rate. I can easily calculate the change in the stock price. I can easily calculate the change in the stock price in the down scenario as well. And now I hope you also understand why I'm not calling the probability of a down movement Q, because then I would have two variables. I call the probability of an up movement P and the probability of a down movement 1 minus P, because now I have one equation in only one variable. The one variable is P, everything else I know. Take an educated guess what the next step is. We solve for P. And once I have P, weird phrasing maybe, but once we have figured out this P here, we can fill it in and calculate the value of the call. Okay? So in order to be able to utilize this formula for the call, probability times outcome plus probability times outcome, discounted back to T0, we first need to calculate P, and this is how we're gonna do it. So logically, mathematically, this will be step 1 and this will be step 2. Or if you need an even more fine-grained cooking recipe, I wanna give you that. Step 1 actually has to be calculate. If you wanna make a note, I will be slow enough that you can write this down or review the video then. Step 1, calculate the change, the percentage change in stock price if the price increases. Step 2, calculate the percentage change in stock price if the price decreases. Step 3, set up this equation and solve for P. Step 4 and last step, fill in the risk-neutral probability P into the final formula for pricing a call in a risk-neutral framework. It always works, no exceptions. The end. That's how it's done. Okay? I stress here what I already mentioned. Risk-neutral probabilities are not physical probabilities. Okay? I cannot stress this enough. I would encourage you to just Google the term risk-neutral probability and interpretation or something like this, that you get a bit of a better sense what it is. It's a very deeply abstract concept. Why? Well, because finance very often, especially derivatives, are, as you already know, very abstract. Okay? All right. Let's actually do it. We do the same example as before. And the reason for that is, of course, it's a didactic reason. I want that you see it doesn't matter if you replicate, if you use the replicating portfolio method or the risk-neutral pricing method, they yield the same results. So we again look first at a 1-period model. I have on my slides also a 2-period model. What else do we have? We have a call option again with a strike of 50. It will expire in 1 period, so it's a 1-period model only. The current price of the underlying is 50. Again, this here is S0, whereas this here is X, right? Don't confuse the strike and the price of the current price of the underlying. It's just a coincidence that they're both 50. The price again will follow a binomial process, so this is not real life yet. We assume the same interest rate as before, 11%. And of course we only have now one question to deal with. What is the price that we would be willing to pay for this specific call? Okay, we do it exactly as I have described. The steps are as described. We actually want to end up being able to fill in this formula. The value of the call equals probability of an up movement multiplied with the payoff of the call in the up scenario plus 1 minus P is of course then the probability of a down movement multiplied with the payoff of the call in the down scenario. Since this will happen in the future, 1 period from now, I need to discount by 1 period. So this will give me the present value of an expected value, if that makes sense. But I cannot do it because I don't know P. So where does P come from? I set up the following equation. The risk-free interest rate as a percentage equals the probability of an up movement, the risk-neutral probability of an up movement, multiplied with the percentage change in the stock price in the up scenario, plus 1 minus P is of course the probability of a down movement multiplied with the percentage change in the stock price in the down scenario. And logically, I mean, that's conceptually what we want to do. Just logically, we cannot start here immediately. Where should we start? Calculate the percentage changes in the stock price first, then calculate P, and then go into the final formula, this bad boy. Let's do it. As I've told you, step 1 in the cooking recipe, risk-neutral pricing of a call, is calculate the percentage change of the stock price in the up scenario. The stock moves like this. From 50, it will either go up to 70 or it will go down to 35. We concern ourselves in step 1 with the percentage increase in the stock price in the up scenario. So how do I do it? 70 euro minus the 50 euro. It's not a strike, it's the price of the underlying at T0, so S0, divided by 50 to express it as a percentage. Multiply with 100 so that you get a nice and even percentage. And I find if the stock price rises, it will increase by 40%. Boom. Step 2 in the cooking recipe, calculate the percentage change of the stock price or of the price of the underlying in the down scenario. So it will decrease then from 50 to 35. So what does that mean in a percentage? 35 minus the 50. Again, this is the price of the underlying at T0. It is not the strike. 35 minus 50 divided by 50. And I multiply with 100 to get nice and even percentages. Okay, and I find the result is minus 30%. In a full sentence, this means if the stock goes down from 50 to 35, it means it goes down by 30%. Okay, so step 1 done. Let me go back. We have now calculated the percentage change in stock price if the price increases and the percentage change in stock price if the price decreases. Step 1 and 2 are complete. What's then step 3? Step 3 is, of course, figuring out the risk-neutral probability of an up movement, so P, and the risk-neutral probability of a down movement, so 1 minus P. How do we do it? Let me go back. By utilizing this formula. It's the same formula, I've just color-coded it as much as I can. The risk-free interest rate, we know the risk-free rate was given to us as 11%. That will go here. Then we have risk-free rate equals risk-neutral probability of an up movement multiplied with the percentage change if the stock price goes up. So I write 11%, the risk-free rate equals P. I don't know P, that's the whole reason why we do it. That's our variable of interest. But I do know the change in the stock price, the percentage change in the stock price in the up scenario. We've calculated it, it's 40%. So 11%, the risk-free rate, equals risk-neutral probability in the up scenario multiplied with the 40%, plus 1 minus P, which represents the risk-neutral probability of a down movement, multiplied with the percentage change in the stock price in the down scenario. We've calculated that as well, minus 30%. So multiply with minus 30%. And then I simply solve for P. And I find the probability, the risk-neutral probability of an up movement is 58.57%. And then I simply calculate the risk-neutral probability of a down movement, 1 minus P, is 41.43%. Brief sidebar here. In the last years, whenever I teach risk-neutral pricing, students actually handle it quite well. They struggle a bit with if risk-neutral probability is not a physical probability, what exactly is it then? All right. But a lot of students ask me after class or even in class and make it sound like it's my job to explain how to solve here for P. So I can imagine that some of you would struggle with solving this equation, but that is outside of my scope, okay? That's really high school math. I don't want to talk about this. If you find yourself struggling with this equation, then you need to brush up your, basically just your mathematic game. Practice this, okay? That is a step that you always have to go through. So you better make sure that you can do this in 5 seconds, okay? If you struggle with this, you still have all the time in the world. You need to be able to solve this kind of equation. You need to be able to solve here for P, okay? Make sure you can. And if you can't, discuss it in the Telegram group, ask other students, but please don't ask me about high school math, okay? That's outside of our scope. So we have now calculated the risk-neutral probabilities, and now we have all our ingredients in place. We know the percentage change, that's done. We have calculated risk-neutral probability. Let me go back. We have figured out P. We know the risk-free rate. The only thing missing is we need to quickly think about the payoffs of the call in the up scenario and the payoff of the call in the down scenario. But that's nothing anymore. That's nothing. If the stock goes up, the stock price will be 70. We are pricing a call, so that means you have the right to buy the underlying here for 50, the strike. Strike was 50. So what's the payoff then? Well, you would exercise your call. Hey Flo, I want to exercise. You give me 50. I have to give you back the underlying with a value of 70. What's your payoff? 20, of course. How is this in the down scenario? Well, if the stock price goes down to 35, you have the right to buy a stock that's traded for 35 for 50. Would you do it? Of course not. So the payoff of the call in the down scenario is therefore 0. And now we really have all numbers in place and we're as good as done. I go back to our actual formula, this sort of present value of an expected value. Value of the call equals risk-neutral probability of an up movement multiplied with the payoff of the call in the up scenario plus probability of a down movement multiplied with payoff of the call in the down scenario. But this will happen in the future. So in a way, this is a future expected value. So I need to discount it with the risk-free interest rate. Boom, I fill in the numbers. We have calculated P as 58.57%. That is what I fill in here. Multiplied with the payoff of the call in the up scenario, the 20, plus, let me go back, probability of a down movement, 41.43%. So 41.43 multiplied with the payoff of the call in the down scenario, which we have figured out to be 0. And I need to discount with the risk-free interest rate, which was given to us as 11%. So that's why I'm discounting here with 11%. 1 plus 11% to the power of 1. I've just immediately contracted it because I'm lazy. And then you type it in your calculator and you find that the value of the call should be 10.55 euro. I have, just for comparison's sake, I have restated here what our result was using the replicating portfolio method, and it was 10.57. So it's of course then also a matter of rounding. I just want to illustrate that it doesn't really matter if you use risk-neutral pricing or replicating portfolio method, they yield the same results. Okay? What do you think, guys? Yeah, of course.
Well, I forgot what I wanted to ask.
It happens. It happens to the best of us.
Can I ask something?
Of course.
Can we assume that if the risk-free rate is not given and the probabilities are not given as well, that the interest rate is risk-free rate, or is it just in this example?
I did not catch this. Can I assume, you said, can I assume if the risk-free rate is not given?
Yes.
Yeah?
Like, because in this example, the interest rate is 11% and we assumed that the risk-free rate is 11% as well.
Yeah.
So if no probabilities are given, you can't calculate RF in this example.
Mm-hmm.
So can we assume that the interest rate that is given in an exercise is the risk-free rate or not?
Ah, I see. I see. Look, thanks for your question. Yeah. So I want to say two things about it, okay? So number one, I'm wondering which one I should say first. Okay, let me start with the content answer first, okay? Let's go back to the description of the risk-neutral framework. Whoop. So in a risk-neutral framework with all our assumptions in place, dynamic hedging is possible, no arbitrage possibilities exist. Investors are indifferent risk neutral, they are indifferent towards risk. So once all risk has been eliminated, all investors expect to earn the same return. But which return? The risk-free rate. What does this logically mean? All future values grow at the risk-free rate and all present values are obtained by discounting at the risk-free rate. So in a risk-neutral, and that's my answer number one, in a risk-neutral framework, there are basically logically no other returns, no other interest rates, because the only return you could possibly earn is anyway the risk-free interest rate. So whatever, if you look at an example in a risk-neutral pricing example, whatever interest rate you find is the one that you have to use because no other ones can realistically exist. So whatever interest rate you see must be the risk-free rate, because in a risk-neutral framework, that's the only return metric that exists. So that's my answer number one. And my answer number two is this. It's more like a question for you guys. And sometimes when I hear a question like this, I understand why you ask, but I'm also wondering where's that coming from? Because I would never come up with an exam question where a large part of the difficulty comes from that students have to basically read my mind. I give you sort of a random interest rate and make you guess, or I don't know, somehow read my mind what you're supposed to do with it. So I mean this, I'm on the record a million times saying the difficulty of a finance exam, of certainly Celine and my exam, will not come from shitty descriptions where you have to guess what we are meaning. So just to understand what effort we are going through, I've requested 3 PhD students to go through our whole exam, the theory part and the calculation part, to basically test drive it. Is the wording clear? Are the interpretations clear? Do students have to make assumptions? And I said, I want that you are as brutal as you can, so you don't need to worry about these things, okay? I'm really not in the business of screwing you over on the exam. I want that it's a decent exam. Like I said, 25% easy, 50% average, 25% a bit more challenging. We have paid a lot of attention that the exam is doable. There will be no insane time pressure. It's a meaningful exam, okay? So please trust me when I say I'm not in the business of screwing you over by phrasing the exercises in a crap way, okay? So also with a risk-free rate, I would not make you guess. I would make it very clear what are the parameters that you have to work with so that you can really do what you're supposed to do on an exam, show that you can do risk-neutral pricing and not prove that you can guess what I want you to do, okay? Please trust me on this.
I remember my question was very short.
Huh?
Like the 11% risk-free rate, it's like 1 plus R. Can it ever be like perpetual and it becomes 0.11?
It's a, damn, that would have been a super interesting exam question. Yeah, I've never heard this question before. Let me go to the risk-neutral framework. So, Storm, please correct me if I'm misinterpreting your question, but basically you're asking, is it possible that this here, 1 plus risk-free rate, so discount rate, that I discount differently, that I simply divide here by RF, because I'm discounting a perpetuity?
Yeah, true.
Yeah, okay. Are there any thoughts? It's a cool question. What do you guys think? Is that possible?
It's like you are doing this operation over and over in time. Is that right?
Yeah, excellent, Alice. Yeah, you can be more confident. Whenever you say something, it's always right. So be confident. You're absolutely right. So to answer Storm's question, I would say no. So first of all, I've never heard this question, so that should tell you if it happens, it doesn't happen very often. I've never seen it. And if I think about it now on the spot, then you're really putting me a bit on the spot, as you should. I would say it's not possible for exactly the reason that Alice already hinted at. Because you discount a perpetuity in the way you described, so only by dividing with a discount rate, not 1 plus discount rate to the power of time. So the question then becomes really, could this here be a perpetuity? And it can't, because it's a one-time operation. So even if you say it's a call with a very long amount of time till expiration, let's say 100 years, it's still only a one-time transaction. Like Alice said, it's not reoccurring every year. So that can never be a perpetuity, I would say. No. Cool question, Storm. I like it.
Thank you.
Next year I will ask you to help me with exam design maybe. All right, how much time do we have left? No, plenty. I suggest I have a second example here of risk-neutral pricing. It's exactly the same example over 2 periods. For now, I want to skip it. Not because it's irrelevant, but because it's like the 2-period model for replicating portfolio. It's just repetitive and boring. I have it on the slides. I will propose the following. We skip it for now and I'll show you Black-Scholes. You go through the risk-neutral 2-period example yourself. Of course, if there are difficulties, then just in our next lecture, ask me about it and I explain happily. But I would like to show you Black-Scholes because that's the real thing, right? That's real world, no assumptions, it's the real deal. And to make it worth your time, 9 in the morning lecture, and when we're done today, you have learned some model that won a Nobel Prize. So that's not nothing, I would say. Let's go to the Black-Scholes model. It's really used in the real world. Okay, so far we have been simplifying reality. Well, we have made all kinds of assumptions, but the biggest assumption was we have looked at this sort of the timeline as if time were discrete. So basically that we have a point in time, t0, and then we sort of magically hop to t1, to t2. So basically there is no timeline, there are only specific points in time, discrete values. But that's not our real, timeline in the real world. Time is continuous. It's an infinite stream with an infinite increments of time along the line. So that's certainly something we have to incorporate. All right. So the problems of our binomial techniques, replicating portfolio and risk-neutral pricing, I think are quite obvious. Number one, which share price moves according to a binomial tree really? That's the first problem. And secondly, how quickly, how fast would you be able to calculate the value of a call? Imagine a 50-period setting. You have seen how tedious it gets for a 2-period setting. Imagine a 50-period setting. And don't forget, a period is not necessarily a year. It's just a point in time where the stock price can go up or down. So that could be seconds or something like this. All right? So that would be insanely tedious. Okay, so what's then the key rationale, the key conceptual logic of Mr. Black and Mr. Scholes? I think it's really impressive. I think it's beautiful. They have argued that if you cut time into infinitely small increments, smaller than seconds, smaller, then they said it actually is totally plausible to say that there are only 2 possible outcomes for the share price. At any infinitely small point in time, what else could the stock do? Up or down? So they said, okay, let's cut time, not into big periods, 1 year or something like this, but into infinitely small units. And then you could really argue, yeah, it's still a binomial process. So that's important. So what is the conceptual logic of Black-Scholes? And that, I hope you also understand me now a bit better didactically, why I forced you through some unlifelike pricing methods. In essence, the core of it, of Black-Scholes, is you constantly, at any point in time, infinitely, you calculate a replicating portfolio. The only difference is the time increments have become infinitely small. So what Black-Scholes is, when I show you the formula, you will say, holy, but I will show you it is still a replicating portfolio, all right? So that's why you need to understand a replicating portfolio, even though it seems unlifelike and binomial process and all that nonsense. You cannot understand Black-Scholes in any other way. It is, in essence, a replicating portfolio, not just one. You calculate for basically an infinite amount of infinitely small increments of time, replicating portfolios. That's what the core of Black-Scholes is, all right? So what I will try to do, and that's, I hope, how I can add value, I will try it when you look at the math of Black-Scholes, which is the only thing I will show you, it's just a formula. I will try my best to make you see, even though it looks very different, that you can still, within the Black-Scholes formula, see the replicating portfolio. Let's do it. Enough foreplay, boom, this is Black-Scholes. When somebody says Black-Scholes model, Black-Scholes pricing, what do they mean? This here, that is the Black-Scholes model. Oopsie, sorry. For this, a Nobel Prize was awarded, all right? Let's talk about it. So how do you even have to read this? There are a couple of misconceptions I can point out quickly. We're still pricing a call. Why do we... Tell me that. We keep talking about calls. What about puts? I've only shown you how to calculate a call. Why is that? Do you think I personally dislike puts? Why do I never show you anything how to calculate a put?
I think we can always calculate also the put with a call-put parity, right?
Excellent, Michael. That's exactly the reason. I don't care about puts because if I can price a call, the moment I can price a call, I can calculate any put by exploiting the put-call parity. So that's the only thing I need to worry about. Excellent, yeah. So what does this say here? Value of the call equals S. So don't look at this term as S multiplied with N multiplied with delta 1. That is not how you read this. So S is really the share price. I have this also explained on the slides here. It means S multiplied with N of delta 1. Okay, so N delta 1 is one thing. It means you need to look up delta 1 in the table of the standard normal distribution. Okay, so it's not S times N times delta 1. N delta 1 is one thing. It's one value that you obtain by looking up delta in the table. I have that on the slides, of course. Minus, what's this abomination? What is X? Tell me. Excellent. X is of course the strike price multiplied with, sometimes students ask me how can I calculate E? What is E? Tell me, what is E?
Infinity?
No. You are?
It's Euler's number, right?
Yeah, Euler's number, exactly. And if you say, but I don't know Euler's number, that's all right. Your calculator knows, all right? So the reason why we need this is, if you go back to your first year content, if you look at continuous compounding and continuous discounting, you need Euler's number. That's how the continuous time is incorporated rather than discrete time, okay? To the power of minus RF, so risk-free rate, times T. And again, the last term, you have to read as N of delta 2. Again, this is one term only, okay? It's not N times delta 2. You first have to calculate delta 2, and N of delta 2 means you need to look it up in our statistic table. All right. And what I want to show you now is, how is this a replicating portfolio? Look at this, look at my color coding. So we have S is of course the share price. We have that in the replicating portfolio as well, S0, right? N of delta 1 we find here as well. So the whole first term that I've color coded red is the equivalent in a binomial world of delta times share price at T0. So what is all of this here, the green term then? This is the equivalent in continuous time of the amount of money borrowed B. Okay, I have some more interpretations. You can interpret this much more. In case I forget, this is only for students who want to know a little bit about it, but I'm exploiting this for my research on convertibles. When we're done with Black-Scholes in 5 minutes, and you're interested, please remind me, okay? So, stock price we know, strike price we know, Euler's number, our calculator knows, risk-free interest rate we know, time to expiration we know. So what are the two things we don't know? Delta 1 and delta 2. So you cannot immediately calculate this. You first need to calculate delta 1 and delta 2 so that you can look it up in the statistical table then. So how do you calculate then delta 1 and delta 2? Boom, like this. There's nothing to interpret here, there's nothing to explain here. I myself think of this as a very abstract formula that I apply. Because I'm neither Mr. Black nor am I Mr. Scholes, I don't mind at all admitting I cannot derive this mathematically myself. If you can, I would love to have after the course beers with you and you explain it to me, but if you look at the actual Black-Scholes paper, I mean, I just have a panic attack and start crying and that's just not worth it for me. I need you to be able to apply this, and that's nothing. How do we actually do this? There's a cooking recipe. Step 1, calculate delta 1. According to this, natural logarithm of stock price divided by strike plus, just fill in the numbers. Step 2, calculate delta 2. Step 3, look up delta 1 in our statistical table, so the n of delta 1. Step 4, look up the n of delta 2 in the statistical table. And step 5, you have all the ingredients, type it in your calculator, press the button. That is the example where I told you in my evaluations, at some point a student complained and said, we only had easy stuff on the exam like Black-Scholes. That's Nobel Prize stuff. So if at some point you think that's easy, awesome. Okay. What else is important here to point out? Yeah, you see here sigma to the power of 2, sigma to the power of 2, sigma to the power of 2. Let's talk briefly about that. What's sigma squared? It's of course the variance. If you would take the root, so then only sigma, that's the standard deviation. But of what? It is the variance of the continuous returns on the stock. What does n of delta 1 and n of delta 2 represent? This is only a refresher really. You know this all from your first year research skills stuff. You know how to look up stuff in your statistical tables. It's a brief repetition. I have also, let me go fast forward briefly. I have also added, it's not for class, but if you say I don't know anymore exactly how I look up delta 1 and delta 2, the n of in my statistical table, it's a brief repetition, also including what happens if you need a value between the columns, how to figure that out. So it's here. I want to show you an example, simply that you see this is, to apply it is not complicated. Okay? I already mentioned, Black-Scholes is in essence a replicating portfolio. That's it. So you see here, stock price, that's our S, n of delta 1 is our delta, and the whole green term is our amount borrowed. But there are alternative interpretations. So what else can I interpret stock price multiplied with the n of delta 1? And I'm happy to tell you because it allows me to use my favorite English word. It's really, really true. So the whole red term here, you can think of as the extent of the moneyness of the option. What does this mean? Moneyness means the expected amount by which the stock price will exceed the strike price. All right? So when we talk about options, about a call option, let's say you have a strike of 50 and the stock is traded for 70. So you're in the profit zone. A trader would not say, I'm long a call option and currently it is in the profit zone. They would say, my option is in the money. If, let's say you hold a call option with a strike of 50 and the current stock price is 50, a trader would not say, currently the strike price equals the current stock price, so I'm indifferent towards exercising. A trader would say, currently my option is at the money. And last but not least, you hold a call with a strike of 50 and the stock, let's say, is traded for 20. A trader would not say, oh, currently the payoff would be 0, so I'm not exercising. A trader would say, currently my option is out of the money. So the extent of moneyness means how much the stock price is above the strike. So basically how far in the profit zone you are. Okay? Okay. And the green term, what is an alternative interpretation of the green term? Well, it's the present value of the strike price multiplied with the probability that the option will be in the money. What does that mean? Well, if it's in the money, so in the profit zone, it will be exercised. So, and that's super neat. So x, the whole term, x, e, and the bracketed term, that would be the present value of the strike price. And n of delta 2 tells us the probability that an option will be exercised. I want to do it super official because that's why I've created this. I want to tell you how you can connect Black-Scholes to something else. I told you part of my research is convertible bonds. The paper I've uploaded on Canvas. We are currently working on another convertible bond paper. Wait, I removed this. Currently on another paper tracking 100 years of convertible bonds in the Netherlands. So I've told you what a convertible bond is. It is a bond. If you buy a convertible, you give a loan to the company, you become a bondholder, but you are allowed as a bondholder of a convertible to change it into a share if you want, into a stock. So initially you're a bondholder, but as you want it, you can become a shareholder. And we are trying to understand why. So based on finance theory, it's not fully clear why the convertible bonds even exist. So we're still addressing or trying to address the research question, why do companies issue convertible bonds? And we basically say that's not something we've invented, we're using it as well. Convertible bonds are not like one group of instruments because some convertible bonds are more likely gonna be converted into shares than others. So you can look at convertible bonds, not just as a group of one kind of instrument, but you could say, well, what was the idea of the company? Does the company actually want you, the convertible bondholder, to convert into equity? Or would they prefer you to remain a bondholder? So smarter people than us were thinking of, how can we classify convertible bonds then? And this is what we do. I'm not making this up, this is really our research. We have tracked 100 years, every single convertible bond ever issued in the Netherlands in the last 100 years. And for every convertible bond, I have calculated, or I'm in the process of calculating n of delta 2. Why would I do this? Because n of delta 2 tells us the probability that an option will be exercised. And then we said, okay, a convertible bond is a hybrid. So it has elements of debt, but also elements of equity. So we are trying to understand why firms issue this. So we want to understand, do companies think about convertible bonds more as an equity-like tool or more as a debt-like tool? So what we can do now is, because we have calculated n of delta 2, which tells us the probability that it will be exercised, we are classifying convertible bonds in a very simple way. If I look at one specific convertible bond, I calculate n of delta 2. And if n of delta 2 is more than 50%, it tells us the probability that it will be converted from a bond, from a convertible bond into a share is more than 50%. Then we classify it as this is a more equity-like convertible bond. If n of delta 2 of a convertible bond is less than 50%, then we say it is more debt-like. And all of a sudden, we have structure. We all of a sudden can model this mathematically and we identify within the whole universe of existing convertible bonds very different ones. High probabilities of conversion indicate the company really wants equity. That's why the probability of conversion is so high. Whereas if the probability of conversion is very low, then we say, yeah, the company really was actually wanted to get debt, but for whatever reason they couldn't. Okay, so I'm trying to show you that it's really possible to use Black-Scholes in all kinds of different contexts. It's a very powerful formula, all right? Also, maybe if you want to do a master later on, finance, don't forget about this. N of delta 2 is something you can calculate for anything that has a kind of option attached. Warrants, stuff like that. Okay, so this is a very, very handy interpretation. The last thing I promise I will say about it is, do not look at a formula like this as, yeah, it's just some ununderstandable gibberish. Try to do what I'm doing here. Let me go back. Try to sort of color code it and interpret what do these terms mean by themselves. Is there a way to interpret? Can I impart some meaning to this abstract looking math? And here, here you really see this. I saw yesterday with my own eyes that you were really awesome at understanding a replicating portfolio. So when you look at Black-Scholes, don't despair. It's just another replicating portfolio from many more points in time. That's all there is to it, okay? All right, so that's the end of this sort of detour. Sorry, let's go back to Black-Scholes and do one example quickly together. And then it already gets boring. So we are looking at a company that does not pay dividends. That's relevant, and you already know why. Why is it relevant for the Black-Scholes model that the company does not pay dividends? Tell me.
It affects share price.
Excellent, excellent. You're absolutely right, because, whoops, what would happen if the company did pay dividends on the ex-dividend day? The share price falls down, and that would, of course, let me go back to the Black-Scholes formula, that would affect, of course, the variance of the stock price, right, as well as the stock price. So if you calculate Black-Scholes for dividend-paying stocks, you would need to adjust for dividend payments, all right? Okay, so we have a company that does not pay dividends. Awesome, that makes it easy for us. The current share price is $12.585. The share price volatility given as a standard deviation, be mindful, it's a standard deviation, it's not a variance. Standard deviation is 25%. The continuously compounded risk-free rate is 4.38%. What is the price of the call option if the option has a strike of 12.50? And 45 days to expiration. The cooking recipe, I don't even need to point it out because there is only one way to do it, which is what I have on my slides. Step 1, calculate delta 1, the natural logarithm of the stock price divided by the strike. I don't know if you can see this with the camera, but everything is color coded. Plus the risk-free interest rate 4.38 plus, make a note, do not screw this up. What is given here is the standard deviation, whereas our formula calls for sigma squared, the variance, okay? So don't forget to square here. Divided by 2, brief side note here, the 2, that is a constant, okay? That's a mathematical constant, it always is 2, multiplied with t, so the time, 45 days to expiration. Divided by square root of, I suppose you could say standard deviation squared, which is then the variance, multiplied with the time. So we fill in our numbers. All the numbers are color coded, there's nothing for me, unfortunately, to explain. Plug and play, all right? Maybe one thing, time. Don't type in here T45, that you cannot do. You have to type it in the following way, 45 divided by 365 days of the year, of course, all right? So that's the one thing that you have to consider, of course. And, yeah, you have to consider, imagine, it's exam time. Imagine I were to give you this, or not me, that would be a Celine example more, but let's say Celine gives you this. And imagine she just changes the wording slightly and says share price volatility variance equals something. Then you need to, of course, know that the variance is already sigma squared, so don't square it then again. Do you know what I mean? Yeah? Okay. All right. So step 1 in Black-Scholes, calculate delta 1. Step 2, calculate delta 2, which is super easy. I have also a practitioner tip here. You simply take the results, so what you have just calculated, delta 1 minus this term here. It's less relevant if you can do it with Excel, but with paper exams that pays off big time. The term that we need here is exactly the denominator from delta 1. So if you were to do it even on this exam with a calculator, write the result or store it in your calculator of this term so you can easily recycle it here, that you reduce probability of errors. You type it in, whoop, and you get some result. So delta 1 and delta 2 you cannot interpret, some weird numeric values, all right? That's also not what we're gonna do with. The next step is, of course, to look up the n of delta 1 and the n of delta 2 in our statistical tables. Like I said, I'm not gonna go through the process of how to look it up. If you don't remember, check out the slides or go back to your first year statistics course, of course. You look it up, you get the results, done. And we have all the ingredients now to go really into our final Black-Scholes formula. We know the stock price, 12.585. we just have looked up n of delta 1, the 0.572418 whatever, minus the strike x of 1250 times Euler's number to the power of minus the risk-free interest rate multiplied with the time. Again, don't type in 45 days. You have to type in 45 divided by 365. Multiplied with the n of delta 2. So that's the probability that the option will be exercised, sorry, 53%. Type it in your calculator and you get a result. The option premium, the value of the call option, if you will, should be $0.52. That's it. I have here on my slides the statistical tables in case you don't know anymore how to look it up. That's exactly what we have done. What happens when delta 1 and delta 2 is negative? That can of course happen. It doesn't mean you screwed up. It could happen. Sometimes then students are a bit confused. How do you look up negative values in a statistical table? The explanation is here as well. Like I said, this is really first year statistics stuff. So if you want to refresh your knowledge, it's really all here. The end. That's it, guys. That is it, guys. I don't really have more to say. What do you think? Does Black-Scholes does it seem doable to you? It's a cooking recipe. Maybe one small thing. Wait, let me show you that. No, come back. Yeah, whatever. I don't want to screw around with the smartboard now. What is relevant in the end when you go into the final Black-Scholes formula, more relevant on paper and pencil exams, of course. Sometimes students screw up when they type in all those values in the calculator because they don't know exactly where brackets should go. Black-Scholes, in my opinion, is like replicating portfolio, like risk-neutral pricing, something you can practice to perfection at home. So anything on the exam relating to risk-neutral probabilities, replicating portfolios or Black-Scholes, I expect all of you to get full points. Simply because there are operations that always follow the same steps, and it should not occur that on the exam for the first time you ask yourself when you use your calculator or Excel where should brackets go, okay? So I really expect that you perfect this at home, that anything replicating risk-neutral pricing or Black-Scholes is something where you can go through your grocery list as you're doing that. That's the level of preparation I would like to see. Okay, and I hope you see this now. You don't have to take my word for it. You don't have to believe me. You have seen it. That always follows the same pattern. So you can practice this. And I don't know how you are in terms of risk appetite. I like the idea of knowing, well, I have to do an exam that is maybe a bit unpleasant. It's a lot of content and you have other exams as well. But if I already know, that's a big topic. I mean, we talk about this, for 3 lectures already. Yeah, this is going to be in one way or another on the exam. So you already know, if it's up to you, you can put in the effort to perfect this, and you basically know in your mind, you already start with a certain, quite significant number of points, no matter what else you find on the exam. So I think this is psychologically a huge advantage. Anyway, guys, any questions, anything I need to explain again, anything I need to know about? Shoot.
Is the Black-Scholes formula the same for American and European options?
No, they would be modified. They would be modified slightly. Just for clarification for all students, there are 2 kinds of options. You've seen it on my slide sets. I did not elaborate too much on it. They differ. So first of all, American and European has nothing to do with they are only traded in America or only traded in Europe. That's not the reason. They differ. A European option can only be exercised really at the end, at expiration date, on this one date, whereas an American option can be exercised at any point in time until expiration. So an American option gives you much more flexibility, so they also have to be priced slightly differently. I need you to be comfortable with what I have shown you here. I don't need, because I mentioned, for example, Black-Scholes works in the way I showed you for non-dividend paying stocks. You can still apply it also to dividend paying stocks, but you would have to correct. That requires some adjustments. I have not shown you that. In case you're wondering why not. Well, because it's 9 in the morning and we did Nobel Prize stuff in the second year of a non-finance specialized bachelor. I mean, that's good enough for me. I mean, Nobel Prize stuff is really good enough for me. I want that you have a core intuition. If you say, yeah, but I already know later on in my career it will be relevant that I can price call options. Also, when they pay dividends, yeah, then do the finance master and prepare yourself for this kind of career. That's not for the second year bachelor, okay? So I'm ambitious. I want that my students are ambitious, but there is a point where I think it would be too ambitious. And Nobel Prize stuff is already good enough for me. Guys, anything else? Nice. Really good job.
I have a quick follow-up actually.
Shoot.
Does it also work for pricing warrants?
It would work because, so just also for everybody else, a warrant is a call option on a stock, but there's a huge difference. When, let's say, you want to be a long call, so you buy a call option from the short call, from me, so I'm short. And the underlying is, let's say, Microsoft stock. It's a transaction between you and me. Nobody else is involved. The company Microsoft does not care. Nothing will change for them. It's just you and me. A warrant is the same thing, but it's a transaction between you. So you go long a call option and the company itself. So if you exercise it, or when you exercise a warrant, something happens for the company because a warrant gives you the right to buy new stocks. So the moment you exercise a warrant, Microsoft essentially has to issue a new stock, a new share for you. So exercising a warrant causes share dilution. It causes the number of shares outstanding to change, to go up. So a warrant, to some degree, is of course very comparable to an option, and therefore, like a convertible bond, has option elements, and option elements are always in the real world priced with Black-Scholes. It's always Black-Scholes and a little bit extra to adjust for the specific instrument. For example, a convertible bond is basically a bond, a normal straight bond, with a call option attached. So what's the price of a convertible? Well, first I price the bond component like I would price any straight bond, and then I price the option component using Black-Scholes. So that would be the logic that is applied for warrants. If you're interested in warrant pricing, in our book there is a chapter called Warrants and Convertibles. So check it out if you want to talk about it. I mean, outside of the course, obviously. Happy to do it. I've hinted once or twice that I do research on convertibles, so I can maybe say a thing or two also. But it's relevant when I talk about warrants and convertibles. I can only do it while drinking beer, maybe. Brief disclaimer. Guys, really good job, not only today. I think it's really admirable how you handled options. It's easily considered the most difficult part of a course that already is considered rather challenging. And I thought you held up super nicely. I mean, that's impressive. At 9 in the morning, no less. So biggest compliments to you and your discipline. That's not nothing. On the downside, my expectations for the exam, for your exam performance are, somewhere here now. Guys, really good job. Enjoy the day. Go to Celine's workshop, I think on Friday again, and I'll see you next week. And next week is our last week. No matter how tired and exhausted you are, you're almost there. If it's a marathon, you're at kilometer 40 right now. You just need to drag your carcass over the finishing line. You can do it. Super, guys. Have a great day and I'll see you soon, okay?
Thanks, bye.
See you guys. Doei doei.